So we can begin. Thanks everyone for coming for this next installation of the I Can't Believe It's Not Better Monthly Seminar Series. This week we have Ben Bloem-Reddy. He's faculty at UBC in Vancouver in the Department of Statistics. Ben works generally in statistics and machine learning, based on parametrics, recently in deep learning, but also in the past in various areas in those two fields. And his research is really aligned with this initiative. He has thought and wrote about the role of aesthetics in machine learning, and he wrote a position paper for our last NeurIPS workshop, which is up on his website. You can check it out. So we're very excited to have him. This week, he's going to talk about some of the challenges, both I understand practically and philosophically, with latent variable modeling. Yeah, so Ben, take it away. Actually, quick logistics. If you have questions, post them in the chat. And one of us will decide whether it's pertinent. We'll interrupt Ben and ask him, or wait for the Q&A afterwards. Okay, without further ado, Ben Bloem-Reddy.
All right, thanks, Aaron, for the introduction, and thanks to the organizers for inviting me, and more generally for putting on this seminar series. I think it's really important and gives us all a good opportunity to think about important issues that don't necessarily have other venues for discussion. So, and thanks to the audience for attending. I'm going to talk about some recent work on identifiability in latent variable models. And I'll talk a bit about that work itself, but I'll probably spend much of my time sort of painting a bigger picture about why I think identifiability matters. And it's a bit different from, say, classical takes on the issue. And then, hopefully time allows, relate this to some big picture issues in machine learning more generally. Okay, so, all right. So just a brief outline so you know where I'm going. I'll talk about identifiability and latent variable models or generative models. I'm going to use these two terms sort of interchangeably. And I'm going to ask why we even care about this and try to answer it partially through a thought experiment. And then I'll talk about some partial solutions. So this thought experiment will raise some issues, and I'll try to resolve some of those issues. And then in the spirit of this seminar series, I'm going to take a brief detour and talk about a little bit about our research process and going through what ended up being sort of a theory-only paper, but that we tried to make practically relevant. And then I'll talk even bigger picture about some views on structured representation spaces and some sort of quasi-philosophical takes on where this fits in modern machine learning. Okay, so as Aaron said, if you have any questions, please type them in the chat window. I like questions, especially giving a Zoom seminar. It feels like I'm talking to myself. So if you have any questions, just feel free to ask them. Okay. So before I talk about things that I'm going to talk about, I thought I'd briefly mention some discarded topics, because I think there are sort of a whole range of things that this type of seminar allows us to think about that normally we don't have the freedom to think about in our traditional venues. So I iterated a few times, and so I'll just tell you about some things that didn't make the cut. So the first one was why I think everyone in machine learning should learn some measure theory. I'm saying this a bit tongue-in-cheek because I don't think this would be a real crowd pleaser, but I do think it's important. Sorry, Zoom keeps stealing the control of my screen, but I do think this is important. I won't go into detail, but maybe this will be the topic of a future talk. This also would make it easier for me to write papers in conferences. Okay, another one is maybe just a list of reasons why I'm not qualified to give this kind of talk. And I think this is something that I feel in most venues, and that I think a lot of people feel, especially early in their careers. And I'm not sure this feeling ever goes away. Maybe it does for some people, but I decided not to spend an hour talking about that. And related to that, I think we all could use more mentoring, and this is some of the, say, affinity groups are really active in this, and I think we all need more of it. So seek it and give it where you can, and I think we are all better off for it. And then something that I'm really interested in, and I'll touch on a bit in the context of today's talk, is where machine learning fits into the philosophy of science, because I think traditional sort of models of knowledge acquisition and philosophical takes on it are a bit, say, not quite up to the task for how we might fit machine learning methods into the picture. Okay, so I'll just say we're all practicing as a bunch of anti-realists, but we talk about it like we're realists. If that doesn't mean anything to you, that's fine. But I think this is something that we're going to have to resolve as a field going forward, and this is something that that this talk touches on a bit. So, okay, so onto the real talk. I'm going to be talking about generative / latent variable models, and the basic setup here. This will be our model that we're going to use throughout the talk. We have observations X, and we view them as being generated from some latent variable Z, okay, with some noise. And additive noise is the easiest one and the most common one, probably in practice, but everything I'm talking about, today we can relax that additive noise assumption quite a bit, but this is the easiest one to just write down. Okay, and typically our latent variable space or representation space is, something like a low dimensional representation of our data. Okay, some examples, and these models have a very long history going back over 100 years. So some examples are factor analysis. This is probably the original one. Maybe there's some even that predate this, but this one goes back to the early 1900s at least. Linear independent component analysis, or ICA, and more modern examples are, say, the generative part of a variational autoencoder and things like that. Okay, so these things are used everywhere, and they have been used for a long time. So a lot of the issues that I'm going to talk about today are not new ones, but I think we have maybe a new take on them. So just a little bit on why we use latent variable models or these generative models. If you look around in the literature, especially the modern literature on this, typically we sort of motivate them by saying they give us a low dimensional representation of the data, and that has various implications that I don't think are really spelled out that much in the literature, but somehow this is seen as a good thing. They're often seen as interpretable or more interpretable than just the raw observations. These latent variable models explain factors of variation in the data, or latent factors of variation. And then the way we use them, oftentimes there's this assumption smuggled in that in our latent space, this RD, which mathematically has linear structure, it's a vector space. Once we have our representation that we've fit to data, we often start doing things in latent space that are linear operations in latent space that we interpret as having a meaningful translation in observation space. So an example from the disentanglement literature looks at interpretable factors of variation where, say, for an image, if you vary a single component of the latent representation Z, you get, say, something like rotation around the azimuth, and somehow this is seen as a good thing. Okay, so we have various justifications for using these things, and I think most of them are well intentioned and have good ideas behind them. I think we haven't spelled them out quite enough. So I'm going to talk a little bit about where I think we might do better about articulating why we're using them and actually using them for specific things. So this is a thought experiment. It's a highly simplified version of what we might want to do, and this is motivated by two things. One, asking why we care about identifiability, and two, this is motivated by an ongoing collaboration with some computational biologists. So, okay, so in our thought experiment, we have two labs, Lab C and Lab D, and the reasons for those letters will become apparent in a minute, but they're doing science. They're doing something scientific. They have a set of measurements, and these are XIs, okay? So for example, these might be some health outcomes, some demographic covariates, some high dimensional genomics data, could be anything really. I'll say specifically, this is not going to be image classification data unless there's some scientific motivation, but it's not necessarily just image reconstruction. And the idea here is that they have the same data. Let's, for practical purposes, think of this as infinite. There are lots of spots for detailed inquiry here that I'm going to sweep under the rug and just focus on some specific problems with latent variable models. So, so they have the same data. These two labs separately fit a latent variable model, and they would like to perform some activities that we typically associate with scientific inquiry. So for one, we might interpret or try to explain the latent factors of variation, and maybe more importantly, in the context of scientific research, ask interventional or causal or counterfactual questions. Okay, so I'm being really casual here with these causal considerations, and I'll just say again, I'm going to sweep these under the rug because we're not quite ready to address them yet as a field. This is something that a few different groups are working on, I think, quite a few actually. And we're making progress in that direction, but we're not quite ready to say anything specific there. Okay, so step one, both labs fit a factor analysis model. So this is just this is sort of the simplest latent variable model you can think of. And I'm using the simple one because it's easy to talk about, but ideally we'd fit something, say, more flexible. And the idea here is we model our observed X. We take a full rank matrix, we multiply it by the latent variable model, or the latent variable corresponding to X, and we add some noise, okay? And we're gonna model these latent variables as just being drawn IID from some isotropic Gaussian distribution in latent space. Okay, so are there any questions about that basic setup? This is an old model, but this is sort of the easy one to keep in your mind as the mental model. All right. Okay, so both labs, Lab C and Lab D, fit their model to data. I'm gonna wave my hands about how they do that. But let's say they use the same inference algorithm, they have the same data, they get the same marginal log likelihood on the observations. Okay, and if we look at
sorry,
oh,
can you just, so Tom Diedrich has a question that quickly, full rank means the dimension of Z, or?
Yes, yeah, so it's we can it basically has a well-defined left inverse. Yeah, so yeah, does that help?
I think so. I think that.
Okay, good. Yeah.
If there's more questions, I'll interrupt.
Okay. Yeah. Thanks for the question. Yeah. Full rank in DZ. Yeah. Okay. So if we fit both of these labs fit their factor analysis models to data, and they end up with the same marginal log probability of the data. Okay. If we look at the latent variable, the inferred latent variables to their observations, we see that they can get something slightly different. Okay, so I've just marked a distinguished observation in red here. Okay, so they get the same log likelihood, but their latent spaces are rotated versions of one another. Okay, so the blue axes on the right here are Lab C's axes of variation here in latent space, and the orange corresponds to Lab D. Okay, so we have no way of distinguishing these things, and at this point, if these two labs are communicating, they say, oh yeah, we fit our data and we get the same log likelihood, so our models explain the data equally well. I've lost my presenter window. Where'd it go? Okay. Okay, so now they've fit their model, and now they want to interpret the latent factors as it's part of an explanatory exercise. So this might be done by, say, looking at correlations between the components of Z and the latent variables. There are different ways to do this, but let's just say they agree on a way to interpret their latent variables. Okay. So lab C with Professor Cat clearly sees that the second component of Z corresponds to cholesterol. Okay, so far so good. Dr. Dog here in lab D comes to a different conclusion. C2 corresponds to cholesterol, yes, but also age and shoe size. Okay, so which lab is right? It's not really very encouraging because they both give different qualitative explanations of the same data that fit the same model. And they end up with very different interpretations. Okay, I'm going to punt on how to resolve this for a minute here, because I think there's a more important question here that is related but a bit separate, and this involves intervening. So in most, or say many philosophies of science, intervention has a higher status than explanation. How can we use our model to predict the effects of interventions or design interventions to get desired effects? So let's see what happens if we try to do this. So if we start with an observation X and then map it to its corresponding latent variable Z, and then add some intervention. This is just a vector in latent space. So this vector delta is an intervention. Okay, then we map back into data space and we look at what the observed effect is on the data. So do the two labs agree on the observed effect? So lab C decreases C2, comes to the conclusion that there's a longer life. Okay, and this is quantified in some component of the data. Okay, and Dr. Dog here in lab D decreases Z2 and comes to the conclusion that it results in smaller phi. Okay, so we get very different conclusions, both qualitative and quantitatively. And if we actually, when I say quantitatively, we can actually, in this case, quantify the difference in what the predicted effect of the intervention is, and it's in terms of that rotation matrix. And on the next slide, I'll put this down in more detail, but it's in terms of the rotation and scaling of the intervention. Okay, so that we would like this to be 0, okay, because sort of logically they haven't done anything different, but they get something very different as a conclusion. Okay, so how do we resolve this? Well, step 4 here is we step in to mediate, and this is a well-known problem of factor analysis as an identifiability problem. Okay, so our definition for identifiability in this case with latent variable models differs a bit from classical definitions of identifiability in the statistics literature, which focuses on parameter identifiability. We phrase this in terms of recovering a latent variable for an observation. So we get identifiability up to some set of transformations, script A here, if we can transport a latent variable with A and then run it through a generator F, and it's equivalent to a different generator not being transported in latent space. Okay. All right. So in general, there may be many such transformations that correspond to different generators in our model class, and we say our model is strongly identifiable if script A just contains the identity function. Okay. So in the context of factor analysis, it's well known that these models are identifiable up to orthogonal transformations like rotations. Okay, so that we get the same marginal probability of the data for different fits of the latent variable model. Okay, so this just comes from the fact that our isotropic Gaussian is invariant to rotations. Okay, and you can rotate your latent variable distribution and basically compensate for that in your generator matrix and for factor analysis, and you get the same induced distribution on the observations. Okay. So like I said, this is a sort of a well-known problem or issue with factor analysis. It's just identifiable up to these DZ dimensional orthogonal matrices. Okay. All right. Are there any questions about this little bit here? So this is important. Okay. So I'll just point out that in the, say, traditionally in the statistics literature, identifiability is seen as normally used as a prerequisite for asymptotic properties like consistency or asymptotic normality. And most of it, this is a frequentist idea, and it's couched in language about there being true distributions. Okay, and I think this thought experiment highlights what I think is the primary importance of identifiability, particularly in modern settings with latent variable models, and that's just, can we use our models in a coherent way in the process of gathering knowledge? Okay. So do they behave like we want them to when we use them to try to ask questions? Okay, so step 5 here after mediation is conflict resolution, and it turns out since we are now aware of this identifiability problem and this indeterminacy inherent in the model specification, that we can map between these fitted models. Okay, so if lab D and lab C report their fitted factor loading matrices, we can just back out the rotation matrix that we need to map between them. And so for any say delta vector for lab C, we can map that to a corresponding delta vector for lab D. Okay, so we can resolve the conflict that way. In my view, this is maybe not the best solution because this requires lab C and lab D to coordinate and to actually come up with this translation. It still doesn't really tell us how to choose which of those fitted models we should ultimately be using. And this kind of highlights that they're equivalent, and we can go between them and hopefully get the same results. But I think more importantly, for nonlinear generators, if we're not using just a matrix F here, but some neural network or some other nonlinear function, if I have a linear transformation in one latent space and I do this mapping, which we can do, I typically won't get another linear operation in the other latent space. Okay, and that has some problematic implications for drawing the same conclusions qualitatively. Okay. Okay, I think this is my take on it, and this is a little bit justifying after the fact why we did this research, but hopefully we can just eliminate the model indeterminacies in our specification. Okay, so this is not trivial, but we're going to try. Okay, and so the next little bit here comes from a paper that a student and I wrote, student Johnny. It's on arXiv now, and so if you have any questions, let me know. We're going to try to resolve this issue as generally as possible without sacrificing too much flexibility and say data-drivenness that we tend to favor in our methods. Okay, so I've intentionally kept most of the talk light on notation, but we need a little bit here, so let me know if anything's not clear. Just to remind you, our latent variable model looks like this. So we have observations X generated through F from a latent variable and some noise. Okay, And again, we can relax this additive noise assumption pretty easily, but this is just the easiest one to write down. Okay. For the purposes of the analysis here, we also need to assume that the generator F is injective, so that it has a well-defined inverse on its codomain. This is a common assumption in the literature. It is also somewhat limiting in that we're working on relaxing it, but it's far from trivial to do so. Okay, so the general setup here is in terms of our set of generators and our set of distributions on latent variables. Okay, so this will form our model space. And some examples here. So for factor analysis, the example I was just going through, the set of generators are just these full rank in DZ matrices. And then the set of latent variable distributions is just a singleton. It's the isotropic Gaussian, okay? Isotropic normal distribution. For linear independent component analysis, it has the same set of generators as factor analysis, but now instead of just an isotropic Gaussian, they're enlarging the set of distributions on the latent space to be all factorized distributions. So these distributions have independent components in Z. That's where the name comes from. And more recently, generative models like the generator in the VAE, where F is just some set of neural networks parameterized by the weights and biases in the neural network. Again, the sort of vanilla VAE just puts an isotropic normal distribution in latent space. Okay, so this is how we're going to talk about. We're going to form our discussion of identifiability around these objects. Are there any questions here? All right. Okay, so everything is going to, in the end, boil down to indeterminacy sets or indeterminacies of the model, things that the data can't help us differentiate between. And formulating the latent variable model in terms of the generator functions and the latent variable distributions lets us look at how we might form indeterminacies from those components. So using the generators on the left here, basically the only possible indeterminacies that we might form from these generators come from pushing through a generator, FA, and pulling back through another generator, the inverse of it, FB. So these are two different generators in script F. And that just moves one point of the latent space to another. And because these generators are assumed to be injective, this leaves the entire measure theoretic structure of the latent space unchanged. Okay, it's known as a Borel automorphism. They basically leave things unchanged as far as the measure theory is concerned, which is important in the analysis. On the other hand, this is on the right here, we can transport between different probability measures in our latent variable distributions, okay, script P. And these are just push forwards or image measures or transports. These are all different words for the same thing. Moving from one distribution in script P to another, okay? So if we can use A and A inverse as just some generic transport to move between these two, you can think about these as, say, normalizing flows or any other sort of invertible transformation that lets us move between distributions in our model class. Okay, so these are the two possible sources of indeterminacies, and there's nothing here yet that says all of these are problematic or even necessarily any of them. Many of them will lead to changes in the marginal distribution on observations, which would be fine because then we can distinguish between those models. Right? So the things that are problematic are the indeterminacies, or these maps that lead to no change in the marginal distribution on X. Okay. So I'll remind you of our definition of identifiability here. So we get identifiability up to a set of transformations if two different marginal distributions on X correspond to two different generators with some element A from this set of transformations. Okay, and we get strong identifiability if A is just the identity. Okay, if script A is just the identity. So so we have a theorem in our paper that says for a generative model, the only sources of indeterminacy come from taking the intersection of indeterminacies generated from the generators and indeterminacies from the latent variable distributions. Okay, so in words, and this is sort of the practical implication, is that our model indeterminacies, all of them must be transports between distributions in our class script P that can be constructed by pushing through a generator and pulling along another one, pulling back into the latent space as FB inverse composed with FA. Okay, so these are two different generators from our model class, and we can use them basically to move between probability distributions in our class of latent variable distributions. Okay, these are the only sources of unidentifiability. Okay. Okay, so this exposes, I'll relate this to some existing work in just a minute. I'll just say this exposes, I think quite transparently, the sort of two dials with which we might use to control model identifiability. It's still far from trivial to actually do so, but these are the two dials we have to turn. Okay, so some examples in factor analysis. This one has been known for quite a while, just not quite in this language. That as I said before, we get indeterminacies in the form of orthogonal matrices, and in sort of the notation of what I just said there, the factor analysis generators are full rank dx by dz matrices, and the only latent variable distribution is this isotropic normal. So if you take the intersection of the indeterminacy sets here, so this should be a script A here, not the singleton class here. If you take the intersection of the indeterminacies here, you basically just get the linear indeterminacies of the normal distribution, which are the orthogonal matrices like the rotations. Okay, you can do the same thing with non-Gaussian ICA. So if you do ICA but leave out the Gaussian distribution from your factorized distributions, then you can recover sort of another well-known result from the ICA literature that you get identifiability up to permutation and component-wise scaling. And if we try to do this with, say, the basic variational autoencoder, where you have this very flexible neural network class of generators, again, this is sorry, this line is totally broken. Basically, we don't know what the indeterminacies of this thing are, but we do know that it's a big set of indeterminacies. Okay. Okay, so there's also recent literature using multiple environments, and I'll get to this in just a minute. No, this is probably most well known from what's called the identifiable VAE, the IVAE, and another approach using mechanisms, so-called mechanisms in latent space to get partial identifiability results, and they fall out of our framework pretty easily. Okay, and this last one, especially the IVAE result, is important to me because this project started, and I'll talk about this in a minute. This project started when Johnny and I were trying to figure out why the IVAE result actually works like it does. Okay, so I think we succeeded in that. And again, I'll talk about this in a minute, but this was particularly satisfying for me. Okay. So, all right, we have our theorem, but there's this obvious question of how do we use this? And I'll just say in general, it's an open question. So ideally, I'll give you sort of the cheeky answer, which is just make this indeterminacy set as small as possible. So make it the identity function, and then you have strong identifiability. But it's not clear how we actually do this. So this is something that that we're continuing to work on, and I think there's no sort of one right answer here. We don't have a general recipe for doing so, but I think, you know, ultimately it can boil down to some pretty some sort of problem specific ways to do this, and hopefully others find this characterization useful and can use it to sort of get stronger identifiability for their models. I'll just go into one particular one that I think is promising, and one that really I think is worth looking into much more. And this is something that has been appearing in various areas of the machine learning literature recently. Of course, it's not a new idea, but I think it's gotten a bit more wind in its sails recently. And that's using multiple environments or views of the data. Okay, so rather than having just an IID source of observations, we have observations taken from different distributions that we might think of as different environments, like points in time or points in space or under interventional conditions, things like that. But ultimately, we sort of know we have some observations from various environments, and the assumption is that they all share the same generator, same generating function, and then we go from there. So it turns out, and this is the setups that the IVAE paper considered and analyzed in detail. So it turns out that if we fix our latent variable distributions from the start, then we can get strong identifiability. And this means that an observation maps to a unique latent variable, and so we can sort of lose all of this, all of the problems in the thought experiment. So so fixing these latent variable distributions are the only way that we've been able to sort of work out strong identifiability so far. I don't think it's impossible to not fix them, but certainly they have to be constrained in certain ways. Okay. So in a bit more detail there, and this is the setup from the IVAE paper, which I'll talk about this sort of in the context of our research process in more detail in a minute. The idea here is that you have some auxiliary variables or some side information about your environments that's denoted U. Okay, and then we say our latent variable distribution has a density, and it's just an exponential family distribution. And so for each value of U, this might be discrete or maybe even continuous. We map U into the into the natural parameters, and in IVAE they use a neural network to do this, but you might think about various ways to do this. And then there is a U-specific sufficient statistic, and then the whole thing is an exponential family distribution. Okay, so in the original IVAE paper, they simultaneously were learning the generator F along with lambda and T, sort of all in one go, and this was the result that we were trying to understand, is that as long as you have enough environments, so capital K is your number of distinct environments. So as long as you have enough environments bigger than the dimension of your sufficient statistic plus one, you get a pretty strong identifiability result where you can recover your latent variables up to permutations and component-wise scalings. Okay, so this is basically in the realm of ICA. And the key here is that they do this learning in latent space at the same time as learning the generator. Okay. So it turns out, and this is something that that Johnny figured out pretty quickly, is that if we fix T and lambda, so if we fix our latent variable distributions for each environment, then we get strong identifiability. So basically these permutations and component-wise scalings go away if we were just to say fix the sufficient statistics and the natural parameters. Okay, so this might seem like a really big sacrifice in flexibility, but we can actually do this in 2 stages if we wanted to, and I think this is a good idea. So we use these side variables, the auxiliary variables, to impose some structure, so to learn some structure in the latent space, and we do that first, and we can do this, say, with contrastive learning, and then freeze those distributions, those latent variable distributions, and now learn your generator. Okay, so if you do that, you get strong identifiability, and the nice thing about the side information is it can be basically anything, and depending on what problem you're working on, this might have different meaning in the context of the problem. Okay, and I think the one that I think is most interesting and is the sort of the most worth looking into is, say, looking at when the side information represents an experimental condition. Okay, some sort of intervention. You won't always have access to this type of data, but if you do, I think this is a really interesting avenue to try to take. Okay, so going back to the thought experiment, if you were to try to use this framework in the context of Professor Cat and Dr. Dog, we would add a step 0, which is decide on the latent variable distributions. Okay, and this might be a first step of training in your latent space to shape the latent space with auxiliary information. You could also just pick a set of distributions that satisfy certain requirements, and you can look at our paper on arXiv for the details on this. And then once you have those distributions, you can fit the model to data as before, whether it's factor analysis or something much more flexible like a neural network. And then everything that comes after goes like hopefully it should. So you can interpret, you can intervene, you can do other things that rely on these eliminating the indeterminacy in the latent variables and generally agree. Okay, and this is I think is really important for using these types of models as part of the scientific research process. Okay, so it looks like I made way too many slides for the 15-minute talk, but I think this next section will fit. I'm going to sort of in the spirit of the seminar series, I just want to talk a little bit about sort of summarize how this project went from the start to submitting a paper and posting on arXiv. And I won't say the project is finished, which I'm happy that it's not finished, because I think it raised a lot of interesting questions that we can work on now. Okay, so a brief timeline, and this is mostly, I had to look at our Slack correspondence, the Slack correspondence that Johnny and I had going back to last spring, so spring of 2021. And part 1 was sort of casting about, trying to scope a project and see exactly what the interesting questions were. And so April and May of 2021, Johnny and I were interested in working at the intersection of empirical Bayes, meta-learning, amortized inference, and generative modeling. I think there's something interesting there, and ultimately we didn't end up doing anything, that could be considered in that area, strictly speaking. But as we were reading the literature, we came across the IVAE paper, and there are sort of a whole bunch of papers after it that rely on this identifiability result to do pretty interesting things. And so we tried to understand that result, and we became confused. And then we thought we were not confused, and then we became even more confused about identifiability, especially with latent variable models, just in terms of basic definitions, frequentist and Bayesian distinctions, which is a whole mess. Reconciling the sort of classical parameter identifiability and with latent variable identifiability. So just at the start, it seemed like we were in a real bad situation, just understanding the landscape of things. But eventually we started to work our way through it and saw some value in trying to, at least for ourselves, sort of bring some order onto the whole set of problems. And sort of during this time, we decided that the IVAE paper was important. I mean, the identifiability result has been used a number of times, as I said, for I think interesting applications. But we really didn't understand why or how that result works. So there's a nice proof in the appendix of that paper, but we really didn't understand what was really going on there. And so we kind of became convinced that using measure theory could be useful. Phrasing things in terms of distributions and transports between distributions might let us actually see a bigger picture, sort of a generalized framework for things. Of course, I had some doubts about whether that type of analysis would be publishable in a machine learning conference, and the jury's still out on that, but fingers crossed that we wrote that paper at least digestibly. Okay, so just as documentation of this whole process, some Slack excerpts. So the IVE paper, as I said, we thought it was important, and I got really annoyed with it because I didn't understand it. And then this is me having doubts about measure theory being a measure theoretic driven analysis actually being publishable. And this is the balance we ended up taking as well. So most of it's in the appendix, but hopefully it's accessible. Okay, so once we kind of decided that we wanted to understand that result and the way we were going to go about trying to do it, Johnny made really fast progress. I was surprised. I'll say Johnny's a second-year master's student. He's going to continue on to his PhD, but he did a great job with this. And so he worked out the sort of the measure theoretic framework and figured out this, fixing the latent variable distributions will get you a strong identifiability result using what's essentially a very similar proof to what is used in IVAE, just with a bit more of a measure theoretic flavor. And so, that was pretty awesome. And that was over a year ago. And then after that, we got stuck for a long time. So August to November, we got stuck, and part of that was just external interruptions. And I'm including this just to sort of say that these things happen in the course of research. So Johnny was applying to PhD programs and scholarships, and I was teaching in hybrid mode, and this sort of thing happens, and it's not the end of the world. And I think it's easy to lose track of that. In addition to that, despite Johnny's technical progress on the problem, we, and I in particular, didn't understand the bigger picture of how we might generalize away from exponential family latent variable distributions and what was actually happening in latent space. And so fortunately, in September, we submitted sort of an in-progress version of things to a NeurIPS workshop, which made us write a draft, put together a poster. Johnny presented the poster at the workshop and had some interesting conversations with people. And that process really helped us get unstuck and see the bigger picture clearly and see some ways forward on how to turn, sort of these basic results into something a bit more. And so then come February, we think we understand the big picture, and we start waffling about whether we should try to run experiments or try pushing the theory. And at least for the style of research I do, there's a point in every project where this decision has to get made. And I'll just run you through some of the sort of pros and cons of the things we were running through. So running experiments, admittedly, is not a strength of mine, and at this point, nor of Johnny's, but he still has time to come up to speed on that. And I think more importantly, we didn't have any real problems to work on. And this is, I think, important for everyone working on methods or theory. If you don't have a real problem to work on, you have a hard time making design choices. Okay, so you just end up making something arbitrary or imagining what might happen. And this is true even for toy examples. So we didn't have a real problem to work on. And so really interesting questions like how or why we should shape the latent space just sort of didn't have any hard boundaries to think around. And that really helped us see that that's not really the point of this paper. It is the point of ongoing work that we're doing in collaboration with some computational biologists, but that wasn't really the point of the paper. On the other hand, anyone who submitted a paper that is mostly or all theory to the conferences always gets a reviewer asking for experiments, and that happened again anyway, but I think it'll be okay. On the other hand, we can push the theory because it's a relative strength of ours, but it's risky because when you do this sort of thing, you don't really know what the timeline is going to be. And we were still kind of stuck only recovering existing models with our framework and not formulating anything new. Okay, and there's always also this question of whether the world needs more models. I think you can usually justify it, but anyway, it's something to consider. So, okay. So finally, in March to May, we decided, okay, we're going to push the theory and write the paper in the meantime. And in particular, we were trying to use our framework to formulate some sort of novel, strong identifiability results. We tried a lot of different things. I have a notebook full of failed attempts. So we were trying to make connections between IVAE and stuff in the efficient estimation literature with nuisance parameters. And it seems like it should work. The intuition is there, and we just couldn't get anything to work. And that was pretty frustrating. We also took an approach that sort of a version of this ended up in the paper, but we couldn't get this exact idea to work, even though it's really appealing to me, that you have multiple environments, you have a reference distribution, and you transport the reference distribution to your environmental distributions and use that with some group theory to basically mod out any of the indeterminacies. And we got some interesting sort of abstract characterizations, but nothing that we could get to work for strong identifiability. And finally, we hit on this idea that we could use the uniqueness properties of certain transport maps, usually optimal transport maps, to get rid of indeterminacies, and went down a little bit of a rabbit hole with Bernier maps because these things have been showing up more and more in the machine learning literature. And we have a little bit in the paper about actually why it's hard to use Bernier maps. And finally, Johnny hit on this idea of using what amounts to something like a triangular flow. It's called the Knotz-Rosenblatt transform. It's an old idea. And we can use these to get strong identifiability just with a single environment. So I didn't say anything about that earlier, but these things we're pushing on a little bit to try to apply them. Okay. So some takeaways, and I think this will probably be my last slide. Unfortunately, I won't get to the third section of the talk. Some takeaways here are that at several points we made choices that went against what seemed like the easiest path to publication. Just from experience, there are certain things that play well at conferences, but ultimately that seemed like not the best choice for us, and we were guided primarily by this desire for understanding and general practical utility. And so ultimately we may end up having a hard time getting this paper published, but the actual research experience was much more satisfying, at least for me. And the end result also, the paper, I'm much more satisfied with what we wrote than I think the alternatives that could have been. And I think we ended up with I think we wrote as close to the, sort of our best paper that we were capable of. So the takeaway here is find what guides you for your research, and don't discard, the path that seems most interesting and most satisfying to you, even if it's not obvious that it's going to get a paper published. Okay, there's some risk there, and that's something we need to, I think, foster more in the field, but we can all do this personally. And then the other thing is that when you get stuck, and everyone gets stuck, sharing with others helps. So write up what you know, try explaining to a non-expert. My partner has played a significant role in my research back to my PhD, where I try to explain things to her, and she asks the best questions, even though she is not an expert by any means in this stuff. And and it always helps me see what I don't understand. And so that's all part of sort of workshopping your work. So submit stuff to workshops, organize workshops. When you go to workshops, be generous with your time and your ideas. And I think we can all benefit from that. Okay, so I'm going to stop there because otherwise I'll run over time by about a half an hour, and I'm happy to take questions. I'll post all of these slides, or I'll share all these slides with the organizers. So if you're interested in hearing or seeing some bigger picture thoughts, then take a look at these slides, and I'm happy to chat with anyone offline if you have any questions. So I'll just stop there. Thanks.
Thanks, Ben. So we have a question in the chat. So, and this is the Q&A now. So for people that have questions, either raise your hand or you can type them in the chat, and I'll read them out. The first question. So Saurabh has a question, and I actually had a similar one. So in the slide where the cat and the dog are in the sort of the solution slide, the solution was that the Dr. Cat and Dr. Dog are going to now sort of decide on this set of distributions over Z. Can you describe, so Saurabh's question, can you describe a bit more what you meant by fixing that set? So it's sort of deciding between them, right? Yeah.
So, I mean, the easy way here is just to use the results from the theory that basically with the IVAE result, basically what you need is for these natural parameters to span to form a full basis of your latent space, and then you get strong identifiability. So one thing you could do, I don't think this is the best solution, but one thing you can do is just say, put your natural parameters sort of at basis vectors. Choose a basis for your latent space, put your natural parameters there, and then you're done. That has certain implications about the structure of your representation space and what a linear transformation in representation space actually means, right? So you might be interpolating between these different environments, and if you're not careful, you can end up with nonsense. It really depends on what your auxiliary variables are, right? So you might think of these different U's being, say, intervention values of an intervention variable, and again, depending on what your sort of objective is, different structures will get you different things. And this is actually the content of the third part of the talk. I'll see if I can. So for example, we might want to represent interventions, okay? And this is something that actually has been done, at least what I'm aware of, a paper in the genomics literature, where they sort of embed these different, they have cell gene expression data that they use a VAE to put them in latent space, and these are different cell types. So these different colors correspond to different cell types, and then the shapes correspond to a particular perturbation or an interventional condition on all the different cell types. And then they use this sort of global delta here as representing their intervention. It's just a linear shift in latent space. And then they use this, so they fit this to some observed data, and then they use this inferred delta to predict the shift on a new cell type that they've held out, basically, that they might predict on. So this is not, the way they've done this is not identifiable, but you can imagine trying to do this in an identifiable way. So I'll just say this is an open question. I don't have sort of a catch-all answer for this, but I do think that using side data is a really good way to go about doing it. But this is something that Johnny and I are continuing to sort of flesh out as time goes on, is what does it actually mean, and how should we go about structuring our representation space? And the structure is really imposed by how we fix our latent variable distributions. Okay, so you can think about different ways to fix them and endowing different structure in your latent space. And again, it depends on what you're trying to do. So
So just, I mean, concretely, like is an example sparsity constraints. Like that's sort of I think of that as sort of the classic way to constrain your latent variables distribution to gain identifiability. Is that an example?
So that, yeah, that is an example. It's not clear to me how to interpret that. That's probably my shortcoming more than the method's shortcoming. But sparsity is something that, yeah, classically and even more recently, people have kind of leveraged that to get identifiability, and that actually does fit in this framework of indeterminacies, because when you put sparsity constraints on things, you basically limit the types of, or say the dimensions of the transformations that you can use to for unidentifiability. Yeah, but again, I mean, I guess this is the thing. We have mathematical ways to get identifiability, but it's not clear that any of them are meaningful in any particular application. And sometimes they are qualitatively. And I think what we really need to do is try to make this as precise as possible. So this is something that we're working on. And I put this slide up here that symmetry transformations are sort of one very general way of doing this type of thing. That so for example, you might want your representation to be invariant to some transformations in data space, and so data augmentation works, and you can compress things. This is something we did just for compression, and then downstream tasks that are invariant to these transformations, you don't lose anything for them. There's some recent work out of Tübingen in the Scholkopf group that kind of augments this with, okay, you have an invariant subspace and then a subspace that is sensitive to certain variations. So you can kind of see how this is all heading in a certain direction, but there's still work to be done to really make this precise and sort of get what we want out of it.
So, I mean, just closing the loop to the question is, so is the idea that, like, before models are fit, these two labs will sort of shake hands on a sparsity constraint or something, they're going to shake hands on some kind of, constraint that's going to make sure that their models don't require, are limit the indeterminacies in the same kind of way.
Yeah,
is that sort of
yeah, it could be a handshake, or it could be like something that you publish your method with, as saying, here's how we structured our latent space and here's why we did it. I mean, it gives you a language for talking about it. In the past, say without this separation, it's just like, okay, we fit everything at once and here's what it is, right? And so if we can really make this precise, say using contrastive learning or sparsity constraints or whatever your constraints are that you can try to justify in the context of your research problem, then that's something we can all reason about. And yeah, maybe it's a handshake. Probably more realistically, it's something you publish alongside with your paper. You can also, if you're using, say, a neural network or any sort of functional embedding of your side data into latent space, you can just create an artifact, a research artifact that lets people use the same thing, and they get the same latent space as you had.
There's a question in the chat from Powell. It's long. I'll read. So the identifiability results you mentioned, like IVAE or contrastive learning, assume that you have a fixed latent space and you try to find a group of good automorphisms of latent space Z, in your case compatible with the generators and preserving the prior. Do you have any thoughts on comparing models with different latent spaces? E.g., it may be hard to say a priori whether the latent space should be models of 10 or 11 dimensional.
Yeah, so this is a great question, and I have to say I don't know. I think there are ways forward here. If you want, you can think about having, say, coherence across dimensions, so that your 10-dimensional latent space is a subspace, a proper subspace of your 11-dimensional latent space, and consistency in the marginal distribution, sort of a stochastic process type consistency. You can think about doing that. We haven't worked that out, but I think it's an important one. And I mean, this is the type of thing that Bayesian nonparametrics was trying to do for a long time and succeeds in some ways. but ultimately we haven't gotten satisfactory results using the types of methods we sort of guarantee us this consistency, and also gets us the expressiveness that we want for a lot of these applications.
Great. Okay, so I think we're a little over time now. If there's any last minute questions, people should raise their hand now. Otherwise, let's thank Ben with, I guess, virtual applause. Or but yeah, thank you very much for this talk. This was great. And if you mentioned that you'll release the slides. We'll post this recording to YouTube, and maybe in the comments we can link to the PDF, to the slides, with the extra slides.
Yep.
Yeah. Also, matter of thing, if you're still here, you should sign up with our mailing list, which you can find on the website. And look out for other things like our workshop and coming up at NeurIPS and whatever. Anyway, Ben, thank you so much. Yeah, look forward to the recording.
Okay, thanks a lot for having me, and thanks everyone for attending.